Welcome to Black. Don't forget to subscribe. The air inside the Hyatt Regency atrium in Kansas City was thick with the sounds of a big band orchestra and the rhythmic shuffling of over 1,600 people dancing. It was July 17, 1981, a Friday evening where the city's elite and everyday citizens gathered for the weekly tea dance. The atmosphere was electric, a celebration of modern elegance in a building that represented the pinnacle of late 70s architectural ambition. But in a single heartbeat, the music was replaced by a sound so violent and alien that survivors would later describe it as a lightning strike inside a closed room. A deafening metallic pop followed by a low guttural roar of shifting concrete. In less than 10 seconds, two massive steel and concrete skywalks, weighing tens of thousands of pounds, tore away from their moorings and plummeted into the crowded lobby below. The sheer violence of the collapse was unprecedented. It didn't just fall, it obliterated everything in its path, turning a scene of joy into a wasteland of twisted rebar, grey dust and shattered glass. We are starting today with the most horrific structural failure in United States history prior to the 2001 attacks. But what we will discover by the middle of this video is even more chilling. The catastrophe wasn't caused by a massive earthquake, a terrorist bomb, or a freak of nature. It was caused by a simple 1-inch change to a technical drawing, a change so seemingly insignificant that it was approved over a casual phone call. Yet it effectively doubled the load on a set of steel nuts that were never designed to hold it. The Hyatt Regency was not just a hotel, it was a $50 million statement of intent, a monument to the urban square concept that was sweeping through architectural circles at the time. To put that $50 million in perspective, in today's economy, you are looking at a construction cost exceeding $170 million. Completed in 1980, the hotel featured a staggering 40-story guest tower and a sprawling sun-drenched atrium that acted as the heartbeat of the complex. The crown jewels of this atrium were the three skywalks, marvels of suspension engineering that seemed to float in mid-air. These weren't just narrow corridors, they were 120-foot long, 12-foot wide bridges of steel and concrete designed to allow guests to transit between the tower and the mezzanine while looking down at the spectacle below. To visualize the scale, each of these walkways was roughly the length of 3 standard school buses parked end to end. They were suspended from the ceiling by a series of 1.25-inch diameter steel hanger rods, which looked like thin, elegant needles compared to the massive volume of the space they occupied. The engineering specifications were, on paper, breathtaking. The second, third and fourth floors were connected by these bridges, which were offset to create a sense of dynamic movement within the 50-foot high atrium. The total weight of the fourth-floor walkway alone was approximately 64,000 pounds. That is the equivalent of 15 fully grown African elephants hanging by threads of steel. When you add the weight of several hundred people standing on those walkways to watch the dancers below, the load capacity requirements become astronomical. Engineers calculated that the steel rods needed to have a yield strength capable of supporting not just the dead weight of the concrete and steel beams, but the live load of a moving, dancing crowd. The public saw a futuristic open-concept masterpiece. The engineers saw a complex web of tension and compression, where every bolt and every weld had to fight against the relentless pull of gravity. Shattering the assumption of safety is perhaps the most difficult part of this story. We often walk into modern skyscrapers, airports and hotels with an implicit trust in the invisible hands of the engineers who built them. We assume that because a building is open to the public, it has survived the most rigorous scrutiny humanly possible. The Hyatt Regency was no exception. It was designed by GCE International, a respected firm with a history of successful projects. It was constructed by Eldridge Construction, a company known for its reliability. The blueprints were reviewed by city inspectors. The steel was certified, the concrete was tested, it was a Class A facility, a flagship for the Hyatt brand, and it had been operating for a full year without a single tremor of concern. The tragedy of the Hyatt Regency is not that it was a cheap or shoddy build in the traditional sense, it was a high-end, professionally managed project that met every legal requirement of the time. Yet, as the band played on that Friday night, the structural integrity of the fourth-floor walkway was already failing. The steel hanger rods were quietly screaming under a stress they were never meant to handle, and the legal and certified nature of the building was about to be proven irrelevant in the face of a fundamental law of physics that had been ignored in a draft room hundreds of miles away. To understand why the Hyatt Regency collapsed, we have to look past the velvet curtains and the sparkling chandeliers and peer into the blueprints of the Jack D. Gillam & Associates engineering firm. The original design for the skywalks was elegant in its simplicity. It called for a single set of continuous steel hanger rods, each 46 feet long, to run from the ceiling of the atrium straight through the fourth-floor walkway's box beams and down to the second-floor walkway. In this configuration, the fourth floor and second floor walkways were essentially independent passengers on the same rod. Each walkway would only transmit its own weight to the rod. It's like two people holding onto a vertical rope at different heights. The rope feels the total weight, but the person at the top isn't supporting the person at the bottom with their own hands. This design met the Kansas City building codes, which required a load-bearing capacity of 151 kilonewtons, roughly the weight of a mid-sized bulldozer, on each connection. However, a massive logistical hurdle emerged during the fabrication phase. Haven Steel Company, the contractor responsible for the steelwork, realized that manufacturing and transporting 46-foot-long threaded rods was a nightmare. These rods were nearly as long as a semi-trailer, and threading the entire length to allow the fourth-floor walkway to be bolted in place was deemed impractical and prone to damage during transit. Haven Steel proposed a minor modification. Instead of one continuous rod, they would use two separate sets of rods. One set would connect the ceiling to the fourth-floor walkway, and a second set would connect the fourth-floor walkway to the second-floor walkway. To a layman or even a rushed engineer, it seemed like a distinction without a difference. They believed the total load on the ceiling remained the same. What they failed to realize was that they had fundamentally changed the physics of the connection. Under the new double-rod system, the fourth-floor walkway was no longer just a passenger, it became a middleman. The rods supporting the second floor were now bolted directly to the box beams of the fourth floor. This meant that the fourth floor beams had to support not only their own weight and the weight of the people on them, but also the entire weight of the second floor walkway hanging below them. By making this change, the engineers inadvertently doubled the stress on the fourth floor connection. Imagine a person hanging from a ceiling bar, and then a second person grabs onto the first person's ankles. The first person's grip now has to hold two bodies instead of one. In engineering terms, the load capacity of the connection was pushed far beyond its yield strength. The yield strength is the point at which a material stops acting like a spring and starts acting like modeling clay. It deforms permanently and eventually snaps. The box beams themselves were a critical point of failure. These were not solid blocks of steel, they were built-up members created by welding two C-shaped steel channels together back to back. To visualize this, imagine taking two staple removers or two U-shaped pieces of metal and taping their open ends together to form a hollow square. The hanger rods pass through a hole drilled in the center of these welded beams, secured by a nut and a washer. Because the load was now doubled, the stress at the point where the nut pressed against the beam was catastrophic. The steel started to undergo local buckling. The bottom of the box beam began to deform, curling inward as the nut literally tried to pull itself through the steel plate. This is what we call shear force, the tendency of one part of a structure to slide past another. What makes this even more tragic is the chain of human decisions. This design change was communicated via a phone call and a few revised sketches. It was never formally recalculated. The lead engineer, Jack Gillam, later testified that his firm did not perform the math on the revised design because they assumed the fabricator, Haven Steel, had already checked it. Conversely, Haven Steel assumed that since the engineers approved the change, it was safe. It was a classic not my job loop that left a ticking time bomb in the hotel atrium. During the final construction, the connection was so weak that it barely met 60% of the required safety code for a static load, the weight of the bridge alone. When the live load of the dancing crowd was added, the angle of inclination of the stress changed, and the metal began to fatigue instantly. We're talking about a structure that was essentially failing from the moment it was finished, held up only by the narrowest margin of structural integrity. The first warning sign wasn't a crack or a groan, it was the subtle, invisible bending of steel that had already reached its limit before the first guest even checked in. At exactly 7:05 p.m., the structural tension that had been building within the fourth-floor skywalk reached its breaking point. For the 1,600 people in the lobby, the first sign of the apocalypse was not a visual one, but a sound. A sharp metallic crack that echoed through the six-story atrium like a gunshot from a high-caliber rifle. This was the sound of the steel box beam finally surrendering. The nut and washer, which were meant to hold the weight of two bridges, literally tore through the bottom flange of the fourth-floor beam. In the world of structural engineering, this is known as a pull-through failure, and once it began, there was no stopping it. The fourth-floor walkway didn't just tip or lean, it dropped straight down, perfectly level for a fraction of a second before it slammed into the second-floor walkway directly beneath it. The combined mass of both concrete and steel structures, now weighing over 100,000 pounds, overwhelmed the remaining hanger rods. The entire assembly pancaked. It took less than 10 seconds for the skywalks to transition from architectural marvels to a multi-ton heap of wreckage resting on the lobby floor. The immediate aftermath was a scene of visceral, high-definition horror that no guest was prepared for. As the dust, a thick, choking cloud of pulverized concrete and plaster, began to settle, the silence was broken by the sound of the hotel's fire sprinkler system. The impact had severed the main water lines, and thousands of gallons of water began to flood the lobby, turning the debris field into a drowning hazard for those trapped beneath the slabs. Survivors described the tea-dance music being replaced by the rhythmic hiss of escaping steam and the frantic screams of the injured. Dr. Joseph Wakerly, the director of emergency medicine at a nearby hospital who happened to be at the event, immediately stepped into the chaos. He described the lobby as a war zone, establishing a triage center on the blood-slicked floor. Rescuers had to use chainsaws to cut through the heavy wooden dance floor and jackhammers to break apart the massive concrete slabs. Because the hotel was built like a fortress, heavy machinery couldn't be brought in easily. They had to use the hotel's own luggage carts to ferry the wounded to waiting ambulances. The human cost was staggering. 114 people lost their lives that evening, and 216 were left with life-altering injuries. These weren't just statistics, they were individuals like 11-year-old victims and elderly couples celebrating anniversaries. The stories of survival were miraculous yet haunting. One man was found alive after being pinned under a concrete slab for several hours, saved only because a void had formed near a structural pillar. But for most, the sheer force of the pancaking effect meant that death was instantaneous. The sheer scale of the tragedy meant that Kansas City's morgues were overwhelmed, and the local convention center had to be repurposed to hold the bodies of the victims. As the sirens faded, the forensic investigation began, led by the National Bureau of Standards, NBS. This was one of the most exhaustive engineering autopsies ever conducted. Edward Prang, the lead investigator, didn't just look at the wreckage. His team reconstructed the failure using sophisticated computer models, a rarity in 1981. They discovered that the as-built design, the one with the doubled rods, was so fundamentally flawed that it barely supported the weight of the bridge itself. In fact, their calculations showed that the connection was capable of supporting only about 30% of the load required by the Kansas City Building Code. It was a bridge that was destined to fall from the moment the last bolt was tightened. The investigation then turned to the paper trail, and this is where the professional disputes became toxic. The Missouri Board for Architects, Professional Engineers and Land Surveyors filed a complaint against Jack Gillum and Daniel Duncan, the lead engineers. The engineers argued that they had been misled by the steel fabricators, Haven Steel, and that the sheer volume of drawings, over 400 for the project, made it impossible to catch every detail. They claimed that telephone approval of the design change was a standard industry practice. The board disagreed vehemently. In a landmark ruling, the judge found the engineers guilty of gross negligence, misconduct and unprofessional conduct. It was determined that as the engineers of record, the ultimate responsibility for the safety of the structure rested solely on their shoulders. They couldn't delegate the laws of physics to a subcontractor. Both Gillum and Duncan had their engineering licenses revoked in the state of Missouri, effectively ending their careers and sending a shockwave through the entire construction industry. The dust settled on the lobby floor, but the shockwaves from the Hyatt Regency collapse were just beginning to dismantle the very foundations of the American engineering profession. This wasn't just a local tragedy, it was a global wake-up call that fundamentally rewrote the laws of structural responsibility. Before 1981, the division of labor between an engineer of record and a steel fabricator was a murky gray area. Many engineers viewed shop drawings, the detailed sketches produced by contractors, as minor administrative tasks rather than critical structural documents. The Hyatt collapse changed that forever. Today, the American Society of Civil Engineers, ASCE, maintains a strict policy born directly from this carnage. The engineer of record bears full, non-delegable responsibility for the structural integrity of the entire project, including every single connection, bolt, and weld, even those designed by subcontractors. This is known as the Hyatt Rule, and it is the reason your modern office buildings and bridges are scrutinized with a level of intensity that would have been unthinkable in 1979. The financial aftermath was just as staggering as the physical destruction. Over 2,000 lawsuits were filed against the hotel, the engineers, and the contractors, resulting in total settlements exceeding $140 million. To understand the scale of that payout, in today's currency that is nearly $500 million, a $500 million penalty for a 1-inch design error. But the true legacy of the Hyatt Regency is not found in bank accounts. It is found in the ethics curriculum of every engineering university on the planet. The collapse is taught as the holy grail of professional ethics, a cautionary tale about the normalization of deviance. This is a psychological phenomenon where people become so accustomed to small, harmless shortcuts that they eventually stop seeing them as risks. The engineers in Kansas City didn't wake up intending to kill 114 people. They simply became comfortable with the idea that someone else was checking the math. It was a failure of the Swiss cheese model, a theory where multiple layers of defense all have tiny holes, and on July 17, 1981, those holes lined up perfectly. The irony is that we had seen this before. In 1907, the Quebec Bridge collapsed during construction, killing 75 workers because a lead engineer, thousands of miles away in New York, insisted on using his own calculations over the concerns of the man on the ground. We didn't learn then. In 1879, the Tay Bridge in Scotland plummeted into the sea because wind loads weren't properly calculated. We didn't learn then either. The Hyatt Regency was a mirror of systemic decisions where the pressure of a construction schedule, the need to get it done, overrode the absolute necessity of a peer review. Every time you walk across a suspended walkway in a modern airport or mall today, you are benefiting from a factor of safety. This is an engineering buffer where a structure is built to hold 3 to 4 times its maximum expected weight. In the Hyatt's 4th-floor walkway, that factor was effectively 0.6. It was failing even when it was empty. Philosophically, this disaster serves as a chilling reminder of the fragility of human ambition. We build higher, wider, and more elegantly than ever before, but our structures are only as strong as the communication between the people who design them. The Hyatt Regency, now operating as a Sheraton, stands today as a beautiful, safe, and fully renovated hotel, but if you look closely at the atrium, you will notice something different. There are no suspended walkways. The current bridges are supported by massive, visible concrete pillars that go straight into the earth. It is an architectural admission of guilt, a permanent physical reminder that when we try to cheat the laws of physics for the sake of aesthetics, gravity always wins the final argument. We must never forget the 114 lives lost, not as a tragedy to be mourned, but as a lesson to be studied. Engineering is not just about steel and concrete, it is a sacred contract of trust between the builder and the public. When that contract is broken by a single phone call or a skipped calculation, the results are written in blood. Thank you for joining us for this deep dive into the mechanics of tragedy. If you found this analysis valuable, hit the like button and subscribe to the channel for more deep dives into the world of engineering and human history. For today's discussion, who do you think holds the ultimate moral responsibility